Okay, so then I just want to share with you to enable doing this homework. Let's take a look at group delay, what it really means. So now this is a kind of a realistic example, of designing a digital game. Okay? So we're going to learn the trick to place zeros and poles exactly where you want. That's kind of what we're doing for this semester. Okay? Putting zeros and poles somewhere on the complex plane. So here you're seeing an example with, let's say, I'm running out of my battery. We're seeing a pole right here, right? That's one pole. And so wherever we put a pole somewhere not on the real line, if they don't occur on the real line, we put a conjugate so that we keep all the coefficients real. Okay, and same thing here. We have actually in this exact example, there is a number 2. Okay, number 2 means that actually in this case we have a double root. Double root for that number. That's not super important. And here in this example, we have a 0 exactly on the unison. In this example, a 0 exactly on the unison with the force and its conjugate equation. Okay. So we are going to see the phase response and magnitude response of this LTI system. And so here on top, we have the phase response strictly in between minus pi and pi. Okay? Strictly, this is what I mentioned. And so this is, yeah, of course, well defined. We can always pick an angle between minus pi and pi so that the phase exactly so that the phase match is exactly the phase of our H of T omega, H of J omega. Okay, so that's doable. But here's the result of unwrapping. Okay, here's the result of unwrapping. Because of these rapid changes here, the phase, we can just extend the range of phase to beyond 2 pi. Okay? Unwrapping so that the phase response becomes continuous. And when it becomes continuous, we can take the first derivative to calculate the group delay. Okay? Because now we have a continuous smooth function, smooth phase response. And the result turns out to be here. Right? The result turns out to be here. So this is a group delay. Okay, GRD stands for group delay. Okay, GRD, group delay. And the function of frequency. And of course we have because all the coefficients are real, actually we expect the phase response as well as the magnitude response. This is the magnitude response. Okay? We expect that both of them to be symmetric because our system, all the coefficients are real. Okay? So the actual frequency goes from DC in the middle. DC in the middle to Nyquist at pi. Okay, so this is actually where we really want to look at the frequency response because now all the coefficients are real. Any questions here? Okay, so you notice that here, if we just go a few slides back, okay, here we have a 0. Remember that on the side we have a 0 and exactly at the frequency 0.8 pi. You get about 0.8 pi. A 0 over there, which means that the gain should be 0. Gain is exactly 0 because the input is at that frequency, 0.8 pi. If the input is at that frequency, the gain is 0. It's going to be cancelled out by the system. Okay? So that's that. But interestingly, the group delay, for the group delay, we see that when we place a 0, the group delay really becomes negative. And this could be strange. That's exactly what I mean. Is there a contradiction? Okay. Is there a contradiction for a causal system to have negative group delay somewhere in the frequency response? That's the question. Is there a contradiction? I want you to think about it. But this is one example. Indeed, in this example, due to the presence of 0, actually generally, we're going to show you in a moment, generally, due to the presence of 1, 0, we expect the group delay to sometimes go to negative. The group delay indeed can be negative. And the answer is there is no contradiction. So how to compromise? Okay. Seemingly there is a contradiction, but there is not. And that's how I wanted to think about what's the reason, how to resolve this seemingly contradictory concepts. But anyway, so let's put aside that negative delay. I want to show you, keep showing you this example. Suppose that now we have a signal. Okay, now this is a signal we have. So this signal, if you take a look, it consists of 3 packets, right? Send the phone call, 3 packets, and within each packet, the detail, the oscillation frequency is different, right? Which one has the highest frequency? The first one has the highest frequency, right? And this one has the lowest frequency, and this one is in the middle. Okay, the signal consisting of 3 packets and each with different frequency. And you take, and this is very nice. You just take the DTFT of the signal. Okay. What do we see? What we're seeing here are 3 peaks corresponding to the 3 packets. 3 peaks, and each of the peaks, this first one probably corresponds to the one in the middle. Okay, because its frequency is the lowest. And the second peak is probably the one to the right. And the third peak is the one that has the highest frequency. Because that's how we kind of make sense of the spectrum, the magnitude spectrum of our signal. Any question here? So that's simply how we make sense of the spectrum. Okay. So if we continue, then let's ask a question: what kind of signal do you expect at the output of this system? If this is the input, what will be the output? What will the output look like? And we are going to see in a moment that each of them will be subject to, be subject to different group delay. Each of them is at a different frequency, right? And group delay is a function of frequency. So because each of them has a different frequency, we should expect each of them to have a different group delay at the output. Okay? So kind of take a mental picture of this: a high frequency, low frequency, middle frequency. That's the order. So at the output, it turns out the order is changed. First of all, you see that we only have 2 packets here. It seems that only 2 are left, but actually not, because the first one is right around here. And that's the highest frequency. The highest frequency now comes to the, maybe right here, okay, maybe somewhere. Okay. But it almost disappears. And the reason is that that frequency is exactly the frequency of the 0. And we have, in this design, we have exactly a 0 on the unit circle at 0.8 pi. But remember that we have a 0. We do have a 0 at that frequency. So the meaning of 0 is to cancel out exactly any signal that is at that frequency. Okay? So the signal, the component at the highest frequency now is completely canceled, almost completely canceled. Okay? And that makes sense. And how about here? Remember that the low frequency occurs before the middle frequency, right? But now at the output, this is the output y of n, the order is changed. So I want to show you this as a nice example, that this is how one way you can change the order of kind of switching the order of the packet. Might be useful for communication, might be not, I'm not sure. But this is a theoretical example you can construct. Using the concept group delay, you can change the order of 3 packets by placing your poles and zeros in a clever way. Okay? So we'll cover that more and more. This is a nice example. I want you to start thinking about what exactly is group delay and its properties. Okay? And that's why, to summarize, that's why the group delay is sometimes called the energy delay. Because it shows you kind of, you think of a packet. The packet has energy concentrated at a certain time point. Okay? This packet has an energy at this frequency and which occurs at time near this time. Okay? So this is the kind of we can describe which frequency occurs, the concentration of every component at a certain time. So if you compare that time at the input and output, the difference is group delay. Okay. Let me say that again. So group delay is called energy delay because it really tells you the delay, how much this frequency is going to be delayed by the system in terms of their energy concentration. In terms of their energy concentration, the time the packet will occur. So that's the interpretation. I'm afraid I'm not being really very good. Energy delay. Okay. Please work on the homework. Okay, the kind of yeah, that's what I want to bring this up. Your homework. So anyway, so group delay of a system is the time difference of the output with respect to the input. The time difference of output relative to the input. That's the take-home message. Okay? Group delay is to compare the time. For every frequency, you consider what time it should occur at the output relative to the input. Okay? Just deliver a signal at time 0. And then what time do we expect the signal's energy to be concentrated? Yeah,